This video is on section 3.7, Arguments and Truth Tables. An argument consists of two parts, some premises and a conclusion. It's as if you were in a court of law and you were presenting a case at a trial. Your premises would be any evidence that you produce, and based on this evidence, can you reach a certain conclusion? So a simple example, premise 1 is, I studied for 5 hours or I fail. Premise 2, I did not study for 5 hours, and our conclusion is, therefore, I failed. Now let's talk about this before we get into the truth tables. This is something that I hope is logical to you. This is an or statement, and we know for an or statement to be true, then one or the other must be true. So I study for 5 hours or I fail. I did not study for 5 hours. That's as if we're calling this portion false. Well, if this compound or statement will be true, then this part must be true. If this part's false, this part must be true, and therefore I failed. Now, not all of these arguments can be worked out logically word-wise. We will have to use a truth table, but that is one that I hope is logical to you. So when we do these, we assume the premises to be fact, and we determine if the conclusion does follow from those premises. And the way we will determine that is with truth tables. So the definition of a valid argument: an argument is valid if the conclusion is true whenever the premises are assumed to be true. And an argument that is not valid is called to be invalid. And we want to structure the debate so that we are using valid arguments. So let's take a look at the example of an argument. Now this is how we lay these out. This stands for if P then Q. So we're going to use this example. If I get an A on the final, I will pass the course. So getting an A on the final is P, pass the course is Q. The next statement is, I got an A on the final. That's P. And my conclusion is, I will pass this course. Now this little triangle of dots translates as therefore. So to prove this is a valid argument, we first translate it into a big compound statement. So this whole argument is, if I get an A on the final, I will pass the course, and furthermore, I got an A on the final, so therefore, I will pass the course. So what that translates to in symbol form is this. Now let's explain this. This is if P, then Q, which was this right here, and P, and where the and comes from is that this whole argument goes together, this and this, and therefore I will pass the course. Now you might be wondering, where did this arrow come from? Well, therefore is the same thing as an if-then statement. And then we will do a truth table to verify this on the next screen. So here is our same compound statement. Let's do the truth table on this. We know that P will go T, T, F, F, and that Q goes T, F, T, F. So when I do this truth table using my little shortcut method, the first thing I do is I go through and look for any single letters I can fill in. So I can definitely fill in that P is T, T, F, F. Here's another plain old P, T, T, F, F. And I've got some Q's I can fill in. Those go T, F, T, F, T, F, T, F. So that's just filling in the basics to start. Now let's start using some of the connectives. We need to start inside the parentheses, so I need to work right here. This is an if-then, and the only time the conditional is false is if the premise is true and the conclusion is false. So that's false, and the rest of this column must be true. Now I'm working this with this column for and. The only time an and statement is true is if both simple statements are true. So this is true, and the rest of these must be false. So this blue column is my answer for the brackets. I need to do the blue column with this final black column under the conditional. And the only time the conditional is false is if the premise is true and the conclusion is false. I don't have that situation, so all of these are true. That is our answer column. All of those are true. So do you remember anything about the whole column being true? That is what's known as a tautology. So if you have a tautology, that is how we prove we have a valid argument. So these are your steps, and it might look like it's a whole lot to do, but once you do a couple of these practice-wise, you should be okay. So you use a letter to represent each simple statement like we did for P's and Q's. You express the premises and conclusion symbolically, and you write a symbolic conditional statement in the form of whatever the first part was, and the second, and etc., out to the last premise, and then the conclusion. Construct a truth table. The conditional statement is a tautology and the argument is valid. If the final column does not have all truths, the conditional statement is not a tautology and the argument is invalid. Sounds complicated, but let's do several, and I hope you will catch on. So here's a new argument. I study for 5 hours or I fail. I did not study for 5 hours, therefore I failed. So we start this by coming up with two simple statements for P and Q. I study for 5 hours is P, I fail is Q. So let's write these symbolically. I study for 5 hours, which was P, or I fail, which was Q. The next statement, I did not study for 5 hours. That's a negation of P. And then we draw a line. And the reason we draw a line is that we're down to this therefore part. So there's always a line before you come up with the therefore. I failed. Well, I failed is a negation of Q. So this is my argument, and this is what I call the vertical arithmetic problem. I know it's not arithmetic, but it just makes me think of vertical arithmetic like the old days, so that's what I call this. To write the symbolic conditional statement, what we do is we take the first statement, just as is, in parentheses, and the second statement, then Q. The only other thing I need is to put brackets around this. So, it's lots of steps to do this, but notice once you have written these simple statements, you're just going to write them all together in this big bracket with an arrow to this conclusion right here. And then we're going to do the truth table on this. So let's do our fill-ins. We can fill in plain old P is TTFF. Plain old Q is TFTF. We can fill in not P, which is just the negation of that column. False, false, true, true. And here we are to fill in Q again. True, false, true, false. One tiny little comment, be careful where you write these, because sometimes I write them up too close and then the tail of the Q ends up making that look kind of false, so you might want to set that off just a little bit so that you're not overlapping your letters. So, starting inside parentheses, we're doing or. The only time an or statement is false is if both simple statements are false. So the rest of these are true. So that is my answer column for the or statement. I need to put that together with this column with and. The only time an and statement is true is if both simple statements are true. So right here I have true, true. That means the rest of these are false. So that's where I am answer-wise, right here. For this whole thing, that is the answer for my whole bracketed statement. I need to put this together with this using the conditional. And the only time the conditional is false is if the premise is true and the conclusion is false. I don't have any of that. So this is true, this is true, this is true, and this is true. And look what we have. We have all truths. That makes a tautology, and therefore our argument is valid. And that's the process we will go through with all of these. Standard forms of valid arguments that are worth understanding and or memorizing and or putting on your index card. Direct reasoning says this: if P then Q. If P then Q, and if P is true, what has to be true? Q has to be true. That's called direct reasoning. Contrapositive reasoning is the idea that we know if we start with a statement, the contrapositive is to switch and negate. So the contrapositive is if not Q, then not P. Well, following that statement, this says not Q, therefore what must follow after not Q is not P. Disjunctive reasoning, and the reason this is called disjunctive reasoning is that these both use the or. Remember, that's a disjunction. And this is what I talked to you on the first screen. This is P or Q. If P or Q is true, then one or the other of these must have been true. If this is telling me that P is not true, then by golly, Q better be true. Same reasoning here. P or Q, the whole statement is true, then both one or the other of these must be true. this says Q's not true, that means P better be true. So that's disjunctive reasoning. Transitive reasoning is like the transitive property you had in algebra or geometry. If A equals B and if B equals C, it follows that A equals C. A equals B and B equals C, it follows that A equals C. It's like you can take the B out of there and there's your A equals C. Same idea with the reasoning. If P then Q, and I'm starting with Q again, if Q then R, then I could pretend the Q's weren't in there, and my conclusion is if P then R. I also can write, because of the contrapositive, that not R implies not P. So these are your valid arguments. If you memorize those, you can use those if you recognize those in any of your homework rather than having to write out the truth table. There's a couple fallacies we should look at here. A lot of people think that this works also. This says if P then Q, and Q is true. Does not necessarily mean P had to be true. If P then Q, let's say that was, if it rains, I'll carry my umbrella. I am carrying my umbrella. Does that mean it was raining? Not necessarily. I might be one of those people that uses an umbrella when it's really sunny outside. So it doesn't work backwards like this. The fallacy of the inverse is this. Remember, the inverse is you negate both of those. Not P does not necessarily mean not Q. So that's why that's not true. The disjunctive reasoning, notice this is very close to what this was up here, but these are both nots. This is not a plain old P. You can't assume not Q. I will go to the store, I will go run, or I will go run. I did go to the store. Does that mean I didn't go run? No, because or means this, or both could be true. And transitive, notice the order here, P to Q and Q to R. That order would be to go from P to R. This is reverse order. This is going R back to P, not necessarily true. All right, let's start filling in some of these and making up our arguments. Here's our vertical arithmetic. That's a plain old argument. P or Q, not P, R therefore is what? Well, this is one that we can recognize. Right. This is the one from earlier. P or Q, not P means Q better be true. Not Q means P better be true. And that's exactly what this is saying. This is or. Not P means Q better be true. This is disjunctive reasoning, and it is valid. And what they want you to fill in here is what you would get when you put those statements together. Now, how do we put these statements together? You take the thing that's on the first line, and you put it there. And the thing that's on the second line, and you put it there. Put big brackets around that whole thing, and the therefore is like then, and there's your Q. And that's what you would type to go into that blank. It may be a drop-down menu, and you won't